Welcome to today's deep dive. It is Sunday, August 16th, 2026, and today we are getting into something really fascinating.
Yeah, we've got a great stack of sources today.
Right, so I want you to imagine a scenario. You're going in for an advanced regenerative aesthetic treatment.
Oh, like addressing scarring or hair loss?
Exactly, or even a targeted medical procedure. You're investing in something incredibly cutting edge, a therapy using exosomes to fundamentally repair your tissues at the cellular level.
Which is not cheap.
No, not at all. And naturally, because you are a human being with functioning nerve endings and you'd prefer this not to hurt, you ask for a topical numbing cream beforehand.
Makes perfect sense.
Right. Maybe it's a standard lidocaine or tetracaine or a benzocaine gel. But right there, literally on the surface of your skin, a hidden molecular war is about to break out.
It really is a microscopic battlefield. And, the casualty of that war is the very biologic therapy you're paying a massive premium for.
Which is just wild to think about.
It is. We are looking at a whole stack of sources today. Clinical trials, cosmetic industry memos, Google patents, and they all center on this massive, almost ironic pharmacological paradox.
The paradox being that we spend thousands of dollars on these incredibly delicate exosome therapies, and then we slather on a $5 tube of numbing cream that essentially acts like a microscopic wrecking ball.
A wrecking ball is a good way to put it.
So our mission today is to figure out the workarounds. We're going to look closely at which topical anesthesia formulations actually provide the numbing we need without completely shredding the fragile architecture of the exosome.
And to figure out how to avoid destroying them, we first have to look closely at the biophysics of the exosome itself.
Okay, let's break that down.
We really need to understand its fundamental vulnerability. So we are dealing with naturally occurring biocompatible nanoscale extracellular vesicles.
Nanoscale being the operative word there.
Right. When we say nanoscale, we're talking about a diameter of just 30 to 150 nanometers.
Which is astonishingly small. You're entirely bypassing optical microscopes at that point and relying on electron microscopy just to confirm they're even in the vial.
Exactly. And their entire existence hinges on their outer shell. It's a phospholipid bilayer, highly reminiscent of our own cellular membranes.
Right.
This lipid envelope is their absolute greatest asset. Because it mimics our own cells so closely, the exosome can basically bypass the endosomal pathways.
Meaning it doesn't get treated like an invader.
Exactly. Rather than being swallowed up by a target cell and broken down in a lysosome, which is what happens to a lot of foreign bodies, the exosome's lipid membrane simply merges with the cell membrane.
Oh, wow.
Yeah, it seamlessly delivers its cargo, like therapeutic RNA or signaling proteins, directly into the cytoplasm.
I always picture it like a microscopic, fluid-filled soap bubble carrying this highly sensitive cargo.
That's a great visual.
It is perfectly designed to merge with other bubbles, meaning your cells, but it is incredibly easy to pop if the chemical wind blows the wrong way.
That is a highly accurate way to visualize it. And the surface of that bubble relies on a very specific electrical charge to survive.
Okay.
We measure this as the surface zeta potential. For a healthy exosome, it sits between -10 and -30 millivolts.
So it's got a negative charge.
Right. That negative charge creates electrostatic repulsion. It keeps the exosomes bouncing off each other rather than clumping together.
I see.
But that charge and the lipid membrane itself is highly sensitive to the surrounding environment. For an exosome to maintain its structural integrity, it requires a strict pH range between 5 and 7.5.
So the moment the environment shifts outside that 5 to 7.5 window.
Things start to break down rapidly.
Like how fast?
Well, if we plunge those exosomes into an alkaline environment, a high pH, the electrostatic balance shifts, water rushes in, and the structure swells until it literally physically ruptures. And conversely, in highly acidic conditions, like a pH of 4, the delicate balance of that negative zeta potential is completely disrupted. The excess hydrogen ions in the acid neutralize the negative charge.
And without that repulsion, they just crash into each other.
Exactly. Without that electrostatic repulsion, the exosomes aggregate. They clump together into these useless masses, and the surface proteins degrade.
Okay, so we have established that we're dealing with a highly sophisticated but incredibly fragile lipid soap bubble.
Yes.
And we absolutely need it intact to deliver the regenerative medicine. Which brings us to the core molecular clash. Our industry sources practically scream the warning, lidocaine and exosomes don't mix.
They really do.
So why are local anesthetics so uniquely destructive to this structure?
It really comes down to the chemical identity of the anesthetic. Lidocaine, bupivacaine, ropivacaine, these molecules are amphiphilic.
Meaning what exactly?
It means they possess both a lipophilic or fat-loving tail and a hydrophilic water-loving head.
Oh, so they play both sides of the molecular fence.
Precisely. Which classifies them as surface active drugs or SURFA drugs.
SURFA drugs, okay.
Yeah. When an amphiphilic molecule encounters an anionic phospholipid membrane like our exosome's outer shell, it embeds itself. The fat-loving tail dives into the lipid layer, while the water-loving head stays near the surface.
Oh, that sounds destructive.
It is. By forcing their way into that structure, these anesthetics fundamentally alter the thermodynamics of the membrane. They disrupt highly organized, cholesterol-rich regions known as raft-like ordered membrane domains.
So they are literally prying the structural bricks apart.
Essentially, yes. They aggressively modify the fluidity of the membrane, which markedly increases its permeability. The contents of the exosome simply leak out.
Wow.
Furthermore, at high concentrations, lidocaine is known to induce neurotoxicity and is highly cytotoxic to stem cells.
Wait, really?
Yeah. If a clinic is using human adipose-derived mesenchymal stem cells or their secreted exosomes to promote tissue regeneration, dumping high concentrations of a cytotoxic SURFA drug onto the treatment area is entirely counterproductive.
Okay, wait, hold on. I've got to push back on this. If lidocaine is this indiscriminate lipid assassin that melts cell membranes and triggers cytotoxicity, why is it in every single medical and aesthetic clinic in the world?
That is a big question.
Like, how is it the gold standard for numbing if it's this destructive?
Yeah.
Are we missing something about how it's formulated?
Well, that brings up a fascinating pharmacological irony. Lidocaine's ability to permeate and disrupt lipid layers is the exact mechanism of how it numbs your nerves.
Oh, I see.
Right. Pain signals travel via electrical impulses, which rely on voltage-gated sodium channels embedded within the lipid membranes of your nerve cells.
Ah, so it actually needs to breach the wall to stop the signal.
Exactly. The lidocaine molecule crosses the lipid membrane, enters the nerve cell, and actually blocks the sodium channel from the inside.
Why?
It has to interact with the lipid membrane to do its job. But the drug is completely indiscriminate. It doesn't differentiate between the lipid membrane of a pain receptor and the highly engineered lipid bilayer of your therapeutic exosome.
It just tears through both of them.
Exactly. It shreds the therapeutic exosomes right alongside the nerve endings.
So essentially, we are inadvertently sabotaging our own treatment.
Mm-hmm.
The patient gets numb, but the $3,000 biological therapy is neutralized before it even penetrates the dermis.
That's the reality of it.
And digging into the clinical memos you brought, the active drug, the lidocaine or benzocaine itself, is only half the battle. We also have to talk about the formulation trap.
Yeah, this is where we really have to scrutinize the actual tube of cream.
Right.
The aesthetic industry faces a massive physical challenge with topical anesthesia. If you just pour a fluid solution of lidocaine onto the skin, it just migrates away.
Because of the dead skin cells.
Right. The stratum corneum, the outermost layer of dead skin cells, is a formidable barrier. Standard aqueous drugs have terrible tissue penetration, so pharmaceutical companies have to engineer complex delivery vehicles.
The thick creams, gels, and patches we are so familiar with. Which means they are packed with inactive ingredients to force the active drug into your tissue. Like, if you're listening to this and mentally scanning the ingredient list on the skincare products in your bathroom right now, you're going to recognize some of these culprits.
Oh, absolutely. You'll see an arsenal of chemical helpers in there, emulsifiers, pH adjusters, and most notably, powerful surfactants.
Surfactants, like in soap.
Right. Surfactants lower the surface tension between liquids and solids, which is great for pushing a numbing drug through the stratum corneum. But let's look at how researchers isolate exosome cargo in a laboratory setting.
Okay.
When scientists actually want to break open an exosome to analyze its internal RNA, they don't use tiny scalpels, they use surfactants.
Oh, man. I noticed Triton X100 heavily referenced in the lab protocols for exosome purification.
Yeah, Triton X100 is a classic non-ionic surfactant used specifically in labs to solubilize lipid membranes.
Solubilize. Literally dissolve them.
Yes. The surfactant molecules insert themselves into the exosome's bilayer until they completely replace the lipids, forming mixed micelles. The bubble dissolves.
Wow.
So, when a patient is prepped with a mass-market numbing cream utilizing similar harsh surfactants as permeation enhancers, the cream basically acts as a chemical solvent for the exosome therapy applied over it.
So if I'm understanding this correctly, applying a standard lidocaine cream before an exosome treatment is essentially a double whammy.
Absolutely.
The surfactants in the cream melt the lipid envelope, and the amphiphilic lidocaine molecules scramble whatever structural domains are left.
That is a harsh reality, and we haven't even factored in the pH adjusters yet.
Oh, right, the 5 to 7.5 window.
Exactly. Remember that strict survival window. Many topical anesthetics are formulated at a much lower, highly acidic pH to maintain the shelf stability of the drug.
Makes sense for the manufacturer.
Right. Or, conversely, some compounding pharmacies buffer them to a highly alkaline state to speed up the onset of the numbing effect.
Pushing the environment entirely out of the exosome safe zone.
Yeah, and the consequence of that is rapid oxidation of the lipid bilayer. It completely loses its structural coherence.
It falls apart.
The exosome spills its therapeutic proteins and genetic material directly into the numbing cream on the surface of your skin. The medicine never even reaches your cells.
So the medicine is treating the cream, not the patient.
Exactly. Mixing uncontrolled topical formulations with highly engineered biologics is a disaster.
Man. So if traditional tetracaine, benzocaine, and lidocaine creams are this hostile to exosome stability, how are top-tier regenerative clinics actually solving this? We can't just tell patients to grit their teeth through a painful laser treatment.
No, definitely not.
So what formulations or strategies actually provide the best numbing without destroying the exosomes?
Well, the field is rapidly shifting toward bio-inspired solutions, and the most straightforward strategy outlined in the clinical data is complete separation.
Complete separation.
Weaning.
Forward-thinking practitioners are simply bypassing topical lipid-destroying creams entirely, keeping the chemical battlefield totally clear of the treatment site.
Yes, they are substituting topical anesthetics with systemic analgesia, primarily systems like Nitronox.
Oh, Nitrodox.
Yeah, that is a 50-50 mixture of oxygen and nitrous oxide. It provides rapid systemic pain and anxiety relief for the patient.
Oh, that's smart.
And because it's inhaled and quickly cleared from the body, the local environment on the skin remains pristine. There are no surfactants, no acidic pH buffers, and no surfa drugs lying in wait to shred the exosomes.
That is brilliant in its simplicity. Just bypass the skin altogether. But, I mean, gas isn't always practical, right?
Right.
Some patients can't tolerate it, or maybe a clinic isn't equipped for it.
True.
If a practitioner absolutely must use a topical formulation, how do we stop the anesthetic from shredding the lipids? We clearly have to change the formulation of the drug itself.
Which leads us to a highly elegant formulation strategy utilizing lidosomes.
Ligosomes.
Yes. Researchers are taking the amphiphilic nature of lidocaine, the very trait that makes it destructive, and they're turning it into a structural advantage.
Using the drug's own biophysics against it. I love that. Walk us through how a lidosome differs from a standard cream.
Okay, so standard numbing creams often utilize lidocaine hydrochloride. That is a salt form of the drug.
Okay.
It is water-soluble, but because it carries a positive charge, it struggles to cross the lipid-rich barrier of the skin without heavy assistance from those destructive surfactants we discussed.
Right, the Triton X100 equivalents.
Exactly. However, if formulators use lidocaine in its free base form, the molecule is uncharged and highly lipophilic.
So it wants to interact with fats naturally.
Yes, and under the right laboratory conditions, those free base lidocaine molecules can be coaxed to self-assemble.
Wait, really?
Yeah, they gather together to form their own nanovesicles, tiny spheres made entirely of the anesthetic. These are lidosomes,
The drug physically becomes its own delivery vehicle.
which fundamentally solves the formulation trap. Because the drug forms a stable, self-contained vesicle, the manufacturer doesn't need to pack the formula with harsh emulsifiers and exosome-destroying surfactants.
That's incredible.
The lidosome basically acts as its own percutaneous permeation enhancer. It creates a stable depot within the skin layers, releasing the anesthetic gradually.
Wow.
So the patient achieves profound local anesthesia, but the skin's surface isn't turned into a toxic, surfactant-laden wasteland?
That is incredibly clever engineering. But looking through the patent data and the recent trials we have, there is another approach that sounds almost like science fiction.
Oh, the ultrasound approach.
Yes, it involves ultrasound-activated co-delivery.
It is arguably the most sophisticated approach in modern pharmacology. Rather than avoiding vesicles, researchers are actually using extracellular vesicles EVs, which are essentially exosomes themselves, to deliver the anesthetic.
Wait, they are putting the lidocaine inside an engineered exosome?
They are, but with a highly specific trigger mechanism. Researchers successfully co-encapsulated lidocaine alongside a lipid gas phase transition material called perfluoropentane, or PFP.
Okay, let's break that down. You have an engineered vesicle loaded with the numbing agent and this PFP compound. How do they get them inside without breaking the bubble?
They utilize low-temperature sonication. The sound waves temporarily increase the permeability of the vesicle membrane just enough to load the lidocaine and the PFP without destroying the structure.
Okay.
Once loaded and applied to the tissue, these engineered EVs are completely inert. They just sit there. The lidocaine is locked away, unable to interact with any surrounding therapeutic exosomes or tissue.
So how does the patient actually get numb? What does the perfluoropentane do?
Well, PFP is a phase transition material. At room temperature, it is a liquid, but it is highly responsive to acoustic energy.
Oh.
When the practitioner targets the area with focused ultrasound, the acoustic energy hits the PFP. Through a process called acoustic droplet vaporization, the PFP instantly transitions from a liquid into a gas.
And it expands inside the vesicle.
Rapidly. That expansion physically bursts the engineered EV from the inside out, releasing the lidocaine precisely on demand, exactly where the ultrasound wand is aimed.
That is wild.
The clinical data on this is staggering. This method suppresses calcium activity in targeted neurons with minimum cytotoxicity. You get high spatiotemporal control, meaning you control exactly where and when the numbing happens, without indiscriminately flooding the entire region with free lidocaine.
So instead of putting our delicate therapeutic balloon in a room full of needles, we are turning the needles into their own protective balloons, and we're only popping them exactly when we need to.
That's exactly it. It really is a massive paradigm shift. We are abandoning the brute force method of dumping active chemical mixtures onto the skin and moving toward bio-inspired, precision-engineered environments where the carrier and the drug actually work in harmony.
And there is one final layer to this that showcases just how dynamic biologic therapies can be. We've talked extensively about how anesthetics destroy exosomes, but the literature reveals a fascinating biological counteroffensive.
Oh, yes. Certain exosomes can actually protect the body from the anesthetic.
The protective exosomes. This blew my mind when I read the source material.
It's amazing. Researchers isolated exosomes derived from human bone marrow mesenchymal stem cells. They discovered that these specific vesicles carry a unique microRNA designated as miRNA-21-5P.
And what is the function of that specific genetic sequence?
It is an active inhibitor of apoptosis. Apoptosis is the programmed cell death pathway that gets triggered when cells are exposed to high toxic concentrations of surfer drugs like lidocaine.
Okay.
When a cell absorbs this specific bone marrow exosome, the miRNA-21-5P essentially alters the cell's genetic expression. It downregulates the apoptotic pathways.
It essentially sends a genetic text message to the surrounding tissue saying, do not die.
Precisely. Even in the presence of neurotoxic levels of lidocaine, these specific exosomes shielded the recipient cells, significantly increasing their survival rate.
Wow.
The biologic therapy isn't just trying to survive the hostile environment, it is actively rewriting the rules of engagement to protect the host tissue.
That is the ultimate synergy. So if you are listening to this and you are planning to invest in exosome therapies, the takeaway is pretty clear. Standard topical anesthetic formulations, your everyday over-the-counter or compounded lidocaine, tetracaine, and benzocaine creams, are fundamentally incompatible with exosome stability.
Totally incompatible.
They obliterate the vesicles through a combination of the surfer drugs' lipid-altering biophysics and the brutal surfactants and pH adjusters required to make the cream work.
Right. To preserve that stability and actually achieve cellular regeneration, we have to avoid those formulations. You must insist on protocols that respect the biophysics of the lipid bilayer.
Right.
That means bypassing topical formulations entirely with systems like Nitronox, or ensuring the clinic utilizes surfactant-free formulations like lidosomes or ultrasound-activated targeted vesicles. The environment must remain within that neutral 5 to 7.5 pH window, entirely free of lipid-solubilizing chemicals.
It is entirely about protecting those microscopic soap bubbles until they reach their final destination. But, delving into all this incredible technology, especially the idea of engineering exosomes to carry highly specific instructions, it leaves me with a wildly provocative thought for you to mull over.
Oh. Where are you taking this?
Well, we just discussed loading vesicles with lidocaine and using ultrasound to trigger a numbing effect. And we know that exosomes naturally function as the body's ultimate communication network.
Right.
So if researchers can already isolate microRNAs that tell a cell to ignore toxicity, what is stopping us from isolating a sequence that modulates pain receptors directly? What if the future of anesthesia doesn't involve numbing drugs at all?
Oh, I see. You are suggesting we bypass the chemical block entirely.
Exactly. Why rely on a chemical like lidocaine to physically wedge itself into a sodium channel like a needle popping a balloon? Could we one day engineer an exosome to simply deliver a temporary turn-off pain genetic message directly to our local nerve endings?
That would be revolutionary.
We wouldn't be numbing the tissue. We would just be sending a biologic text message to the nerve saying, hey, ignore incoming signals for the next hour.
Replacing indiscriminate chemical warfare with perfectly orchestrated biological communication. It would render local anesthetics entirely obsolete.
No more molecular wars on the surface of your skin. No more formulation traps. Just a seamless conversation between your cells. Definitely something to ponder the next time you're sitting in the chair wondering what's actually inside that numbing cream. Thanks for taking this deep dive with us.